As usual, the person that has invited the speaker is going to introduce. Today, it's Elena Ferrero from Universidade de Santiago de Compostela. Please, Alessandro.
Yeah, so let me introduce you, Elena. So yeah, she's professor in Santiago, as you can read from the slides. So, and she's a collaborator with people in France. She was visiting professor since 2006 in Orsay. She was working mostly in heavy ion physics and recently with this with understanding the behavior of quarkonia production as a function of the activity of the reaction. And she will talk about how quarkonium can be used as a tool to understand what's going on across all the possible nuclei collisions.
Thank you, Alessandro. So, thank you very much for inviting me to this seminar, which is my first seminar online. And I think that for you is your second seminar at the ECT. So, as Alessandro said, I'm going to speak about quarkonium. Since the beginning, I'm going to introduce some definitions. I will explain to you the main points of the seminar are going to be about the charmonium, either charmonium and bothonium. So the mesons made up of bound states of charm or boson. I'm going also to speak about the quark-gluon plasma, which is the confined matter supposed to exist after the Big Bang. Why we are studying charmonium? One of the main goals is the study of this quark-gluon plasma in the heavy ion collisions. And charmonium was proposed many years ago, in 1986, as one of the signals for this quark-gluon plasma. So the idea is the following. The starting point is quantum chromodynamics, as always. We expect that asymptotic freedom of quantum chromodynamics appears as a screening of the long-range confinement potential at high temperature or high density, with the appearance of new degrees of freedom. It's more or less what is explained in this figure, where you can see the energy density over temperature versus the temperature. You can see that around a critical temperature of 117 MeV, you will obtain a lattice QCD. In fact, calculations obtain a number of degrees of freedom that increases even at the level of the one of or close to the one of a non-interacting gas limit. So the fact is, we are looking for this kind of matter, high temperature and density matter, and where we can find it. Of course, at the universe after the Big Bang, but we cannot go to the Big Bang. We can find it also in the core of neutron stars, but for us, and this is one of the main subjects of study for me, is in the ultra-relativistic heavy ion collisions from SPS up to LHC. The fact is that a lot of people from the theoretical and experimental side have been working on this, and the quark-gluon plasma was firstly announced in 2000 by CERN. The first claim was obtained from data from SPS at around 20 GeV. They collide lead on lead, and they said that there were evidence of a new state of matter, this quark-gluon plasma, and one of the evidence was the suppression of the gypside. The second claim came around 2006, where RHIC at BNL announced that this quark-gluon plasma was kind of was not like a non-interacting gas, but a perfect fluid, a strongly coupled quark-gluon plasma. And at present, at LHC, we are studying always this plasma, this quark-gluon plasma, in different collisions. In fact, the plasma is considered to be formed in nucleus-nucleus collisions, and the other type of collisions, this proton-nucleus or even proton-proton, should be used as the baseline for the confirmation of the quark-gluon plasma. Why quarkonia? Quarkonia as an evidence of this quark-gluon plasma. Well, the idea is, as you know, is that the potential between a quark and an anti-quark pair grows linearly at a large distance, as it is here. But the fact is that if you increase the temperature, like here you are increasing the temperature from up and down, you will have a screening of the long-range confining potential, and you will obtain a potential that behaves like this. Those parameters here corresponds to the radius of the state divided by the lambda d. Lambda d is the device screening radius, which depends on temperature. So the idea is that if the radius of the state becomes larger than this lambda d, you will have different states that will melt at different temperatures due to different binding energies. That was the original proposal for the study of the GIPSI. The idea being that you will obtain different states melting at different temperatures. You could use this quarkonia as a kind of a thermometer of the quark-gluon plasma. That is, again, the same idea. If you have a radius of the state in vacuum, you will obtain a bound state, but in case of a temperature that goes higher than some critical temperature, you will obtain the suppression of this bound state in such a way that you can study a sequential melting where the excited states will be suppressed first. You will have a suppression of the 2s, the Chi-C will be suppressed afterwards, and at last the GIPSI. This idea, which is very nice, is due to Matsui and Satz, that proposed this GIPSI as the signature of the quark-gluon plasma formation. But the fact is that this is an oversimplified picture. The story is not so simple as I will try to show you during this seminar. We have many questions that are not solved, which are the following. The ones that I'm going we have much many than the ones that I'm going to show you now, but at least I will try to answer the following ones. First, if there are any other effects that are not related to color screening, but that may induce a suppression of a quarkonium state. That is one of the questions. Second, if there are effects that can induce an enhancement of quarkonium production instead of a suppression. Also, it is very important, the reference, in order to consider that a state has been suppressed, you need kind of a reference. And one of the questions is if it is possible to define an suppress process in order to study this quarkonium suppression. And at last, do we understand really charmonium production even in elementary proton-proton collisions? That would be the last question. But I'm going to start by this last question. The fact is that we need, and is what my goal in this seminar, is to show you that we need a global picture, including from the production mechanism, from proton-proton, to the medium effects in nucleus-nucleus, but covering different system size and energies. So passing through proton-nucleus. Let's start by the last of the questions. So, do we understand charmonium production in elementary proton-proton collisions? Well, the charmonium or the quarkonium production mechanism is trying to be illustrated here. You will have a production of a heavy quark pair that is perturbative. So this part will be under control, but then you will have an evolution of the QQ barrier pair into a physical quarkonium state, and that part is non-perturbative. In order to explain this second part, you can apply different models. The main three models that are in the market, the main three ideas, in fact, are the following. You will have, historically speaking, the first approach to hadronization came from the color singlet model. Within this model, one assumes that only a physical color singlet state becomes a quarkonium. So the quantum numbers are conserved, and only the pair with the right quantum numbers become a quarkonium state. Effectively, that means that you don't have any free parameter. Second, the color evaporation model that appears is a phenomenological model where all pairs are taken into account in order to produce quarkonia if they have a mass that is less than some threshold. So there is a parameter that depends on each quarkonium state. And the last and most successful approach is the non-relativistic QCD that includes not only the singlet states, but the possibility also to have octet states in order to produce quarkonia. So all pairs of QQ bars are taken into account with various probabilities. You have then the non-relativistic QCD matrix elements that are considered to be universal, so the same for different states, and you will have infinite parameters that are organized in powers of alpha S. The point is that after more than 40 years, the production mechanism, the partonic production mechanism for the production of quarkonia is still not settled. And this can be a problem or not, as I will show you. So first of all, the state of the art in which concerns a proton-proton production at a partonic level for the GIPSI. Well, what you can see here is that all the models are still in the game. This is polarization. These are the cross-sections for the GIPSI production. And you can see that, of course, at high PT, the models that take into account color octet emission agrees better with the data. But the point is that a lower PT, lower and mid PT, which is the region where the quarkonium heavy ion studies are mainly carried out, all of the models agree more or less with data. This is also the case for the excited state of the charmonium, so the 2s, and which again you have still in the game the three models that I mentioned before, and that in the low PT region, low mid PT region, the three of the models can explain the data, and for the upsilon, the situation would be, since the upsilon is a couple of BB bar quarks, the fact that you have higher mass scale would mean that in principle the NRQCD approach would be the one that works, but in fact also the color singlet model approach can reproduce the data if you take into account next to leading order corrections. So the fact is the following, is that as a conclusion of this first part, even if the three mechanisms for the partonic production of quarkonia are still at play, you can use any of them for the production in the low and mid PT region, because all models work fairly well there. Second point, are there any other effects which are not related to color screening, which was the main mechanism that was invoked in order to explain the suppression of the quarkonia, that can also produce a suppression? In fact, in order to study those effects, the collisions as the proton-nucleus collisions were proposed, because in those kind of collisions, it was considered that the quark gluon plasma could not be produced, since the temperatures and the densities are not high enough. That is the initial idea. So, in that way, you could study other effects that are not specific of quark gluon plasma that can also produce a suppression of the quarkonium. The main effects that I am going to mention is the first one, which is the modification of the nuclear parton distribution functions in the nuclei. We know very well that the parton distribution functions of nucleons in the nuclei that don't behave as different nucleons putting all together, as the addition of different nucleons. This is usually called the nuclear PDF shadowing. Another approach to explain this modification of the gluon flux comes from the gluon saturation model, particularly for the color glass condensate. This corresponds to initial state effects that should be taken into account if you are studying quarkonium. Second, you have another kind of effects are the energy loss or the final state interaction effects that also can produce a breakup of the quarkonium by the interaction either with the nuclear matter, with the nucleons, or the spectator nucleons, or with the pions that are produced in the collision, which are called the Comover particles. So those effects I'm going to speak in this seminar about the initial ones and also the last ones concerning proton-nucleus, and then we will see what happens for other collisions. These effects are interesting also because they are specific physics effects that can be studied with those, which are, for example, the QCD factorization in media, the quarkonium production mechanism, the octet versus singlet, since some of those effects depend on the state, the partonic state, and also test the dynamics of hadronization and time evolution of the QQ bar pair. A question that can appear and that has appeared lately is the fact that if it is possible to have quark gluon plasma-like effects even in proton-nucleus collision, we will see that at very high multiplicity, even in proton-proton, you can have strange effects, as I will show you. In any case, we need to study this proton-nucleus because these effects are nuclear matter effects are relevant if one wishes to use quarkonia as a proof of the quark gluon plasma, so as a baseline. I'm going to speak a little bit, first of all, of the nuclear PDFs. As I told you, the parton densities in nuclei are modified by the nuclear environment, and the nuclear PDFs are assumed to be to factorize in terms of the nucleon PDFs. The fact is that if you take the nuclei PDF divided by the nucleons ones multiplied by the number of participants, if you obtain here 1, that means that there are no nuclear effects. But in fact, you obtain results different from 1. Here are some of the typical ones that are in the market. There are new ones, NCTEC, EPPS. In any case, they consider they are fits to data that show you the behavior of those nPDFs that show in all of them a suppression at large energy, so small x means large energy. And many of them show an anti-shadowing at small x. You have several PDFs available. The first effect then to be taken into account should be this one when studying proton-nucleus data on quarkonia. We have done this. It has been done by many people. And how to do that? In fact, what you can do is just to study a collinear perturbative QCD framework. You can take those nuclear PDFs And you can also take other effects. For example, the suppression due to interaction with the nucleons. Let's say these two effects as a baseline, and to see how I could calculate quarkonium. You can calculate any differential cross-section if you put here your effects, and also here the partonic cross-section. For the partonic cross-section, as I showed you before, the fact is that since the different models work kind of well in up to mid-PT, you can use any model. And in fact, I used different models, and the results are more or less similar in proton-nucleus. The results will be the following. So here, what do you have? Here you have the suppression of the ground state, so the gypsy in the case of the charmonium, the upsilon 1s in the case of bothonium, compared to the data. The data I don't know if you see very well, but here you have the data, here also. And these are different nuclear PDFs approaches. They give different results, but in any case, what you obtain is a suppression when you go to larger rapidities, so to small x, and also for the bothonium, except mainly in this part that corresponds to large x, to the backward rapidity region. The data are presented as the nuclear modification factor, which is a typical way of presenting heavy ion data, where you take your results, your yields for your collision, proton-nucleus in this case, divided by the results obtained in proton-proton multiplied by the number of collisions. It's a way of seeing if there are any nuclear effects. Consider in this case that you have a right reference in proton-nucleus. That we will see that can be a problem. If it is, this ratio is lower than 1, as it is shown here by the shadowing, that means that you have a suppression. The data is compatible with the strong shadowing in the forward rapidity region, and in the backward region sometimes you have some problems, as here for the upsilon, and this is at LHC energies. The exercise can be done at lower energies, as here, where you need, in this case, to apply other effects for the charmonium. This is deuteron gold data at 200 GeV. And here you can see that without any other effect, the result is too high. But then you will obtain the right effect, as here, if you introduce other effects, that in this case is the nuclear absorption. That means that the gypsy could be destroyed by the interaction with the nucleon spectators that are in the collision. For the upsilon, you have here the results. And in any case, I would say as a conclusion of these nuclear PDFs is that the fact is that the ground state data is fairly reproduced by this kind of interactions, in which concerns just the ground state. So I'm meaning the gypsy or the upsilon 1s at LHC. Okay, but what happens for the one thing that I would like to mention also, because I see before Dionysius connected, is the fact that all the results that I have shown you for the nuclear, for the proton-nucleus collisions in the forward region are also reproduced if you take into account the initial state effects in a different way, as for example, in a saturation model as the color glass condensate. You cannot both use the nPDFs and the color glass. You should choose, are different frameworks, but both corresponds to an initial effect that can reproduce the ground state data. The problems arrive if you try to reproduce the excited states in proton-nucleus collisions. I put here the results that were first obtained by Phoenix, so at RHIC energies of 200 GeV. Then ALICE, LHCb, CMS, Atlas, all of them obtained a relative suppression of the excited over the ground state in proton-nucleus or deuteron-nucleus collision. For charmonium and for bothonium. I am putting here relative means that in all those cases, there is a normalization to the value obtained in proton-proton in order to see if there is a suppression due to nucleus. So these are the results. Here, for example, you have all the results put together by the results by Phoenix, but also putting in the same slide results from LHCb versus the number of particles, so versus the multiplicities. You can see that the data shows that when you do proton-nucleus collision, you will obtain a suppression of the excited state. So this ratio is going to be lower than 1. If you do this study versus rapidity, as did by CMS, here you have differently the two states. You have the gypsy, as I showed you before, so the ground state of the charmonium, and here you have the 2s state, so the psi prime, and you can see versus rapidity. And you can see that in the backward rapidity region, there is an extra suppression of the excited state. Those black points corresponds to the results, more or less to the results I showed you before in the previous slide that were nicely reproduced by the nPDF modifications. So what is happening? That is the problem. And in fact, one could say, okay, this is not new. This extra suppression for the excited states was originally discovered already at SPS energy, so at 20 GeV. But what is happening now? The fact is, okay, the initial state effects cannot be cannot explain that, since they are considered to be the same, identical for all the family. This initial state effect does not depend on a final state being excited or not. A final state effect should be a plane that could explain those results of the extra suppression for the excited states. One of the effects that could explain the ancient results at lower energies was the interaction with the nuclear spectators, this nuclear absorption. But the problem is that now that cannot be the origin of this suppression. There is a common, it is believed that as you go at higher energy of the collision, you have less nuclear absorption, in principle, because you have less time to traverse the nucleus. So there are less interaction with the nucleus, and in any case, this interaction should be the same for the whole family, for the 2s, 3s, and 1s states, since the time is boosted. So at high energy, you have too long formation times. So the charmonium state or the bothonium state is not distinguishable while traversing the nucleus. So this is not nuclear absorption, this is the suppression. So what is happening? Because of this, we thought about an ancient model, which is the interaction with the Comover particles. What are the Comover particles? The Comover particles are particles produced at similar rapidities as the charmonium state, but that have much more time to interact. They have a lot of time to interact with the charmonium since they are traveling along together. In principle, that was Phoenix what gave us the idea to use again those models in order to try to reproduce these results they obtained the first, the relative 2s over 1s suppression in deuteron gold collisions at RHIC energies. So we did using a Comover model that was used a lot in 2000, that was successful in reproducing the results for the gypsy and psi prime by taking into account just the interaction with the medium. Here you have the production of the quarkonium state. Here you have the density of the medium, the density of your Comover, of the pions that are produced together with the gypsy or the bothomonium. And here you have an interaction cross-section. This interaction cross-section was originally fitted at SPS energies. This model was used firstly at SPS energies. You can do an easy interaction, an easy integration, and you will obtain a survival probability if you integrate from an initial time to a final time that are taken to be proportional to the densities. So the last density is going to be the minimum bias density obtained in proton-proton at the same rapidity, at the same energy as the nuclear collision that you are studying, since at that moment we consider that this model was not applied in proton-proton. So in proton-proton, the density of Comovers was not high enough to produce that kind of effect. And here you put the initial densities of the pions that are produced. And we do it with a Monte Carlo, but you can even take these numbers from the experiment. By doing so, what you are going to obtain is that you will going to obtain a stronger suppression, where the Comover densities, where the multiplicities are larger. And in the case of asymmetric collisions, as for the proton-nucleus, this suppression is going to be stronger in the backward rapidity region, in the nucleus going direction. So let's see what's the results. The first results obtained from for a proton-nucleus collision. And that were the results in 2015. This plot corresponds to the results from the model for the gypsy and from the psi prime compared to the data. The data in blue are the gypsy, the data in black are the psi prime. Here you have the initial state effects we see, which corresponds to this line, this black line, and the extra effect. You can see that for the ground state is very small, since the gypsy was considered to have a small interaction cross-section that was fitted, originally fitted in the 2000, and we never changed it at that, to do that, to do this plot. And also for the gypsy has a larger size, has a larger cross-section, so the effect compared to the initial, here is the initial plus the Comover together, is an extra effect that can explain the suppression obtained by Phoenix, by RHIC data. When going to proton-nucleus collisions at LHC, as here, you will have also in blue the results for the ground state, in red the results for the excited state, and you have here this line, this black line corresponds to the nuclear PDF effect. So you can see one thing which is kind of interesting. In the forward region, the density, the multiplicities are not very large. The effect of these Comovers on the ground state is very small, but the effect on the excited state can be important. And in the backward region, the effect on the excited state is very important. It's very important because here you have larger multiplicities. This is the double ratios in order to avoid these initial state effects, and you have the curve which agrees very well with the data. And those results were pretty encouraging since the data were not fitted. We used the same cross sections as originally fitted in 2000. But when we try to reproduce the bothomonium by applying the same effect, the problem was that the bothomonium family is much richer than the charmonium one, and that you have at play a lot of feed-down effects. So if you want to take all these are the feed-downs at low PT, at large PT, for the 1s state, 2s, and 3s states. So, and this information is, of course, fundamental if you want to use bothomonium as a probe of a quark-gluon plasma, because if you want to use bothomonium as a sequential suppression, you need to take into account all the feed-downs. So since we were not studying the sequential suppression, but we wanted to create a baseline for those studies of sequential suppression, we put all the states at play, but we cannot fit all the cross sections. So we introduced an approach that was going to be more microscopical by taking an interaction cross section that depend on the geometrical one. The geometrical one just corresponds to the one that comes that you can obtain with the Quarkonium Bohr radius of the state by solving the Schrödinger equation with the potential. And we put here also the binding energy of the Quarkonium state that corresponds to the difference between the open heavy state and the Quarkonium state, and also the energy of the Comovers. And we do an average of this over a Bose-Einstein distribution of Comovers. Like this, you can obtain all cross-sections you want for all the charmonium states, charmonium or potomonium states. We did by, you have two parameters. You have one parameter here and another here that corresponds to the temperature of the collision. And we did, and the results that were real predictions, in fact, because we didn't have the data at that time, LHCb data, were these green lines without any initial state effects, since we are doing here double ratios. And the results was very good, was not presented by us, but by the collaboration, in fact, as a real prediction. Next, we have to check if putting this effect together with the original shadowing, the nuclear PDF modification, went well. Yes, because the nuclear the effect is not very important for the ground state. So for the ground state, everything worked well. And even here, we took into account those modifications. And here in the backward region that corresponds to here, the fact is that the Comover-interaction, since here you have more multiplicity, goes in the right direction. Next step. That was the result. Sorry, that was the result before putting Comovers. You can see that here the Comovers are low densities, so not a very strong effect. But in the backward region, the effect is here a little bit. For the Upsilon 1s. So only 2 comments to resume this part on proton nucleus and arriving to the things that we are doing now with Alessandro, is that for proton nucleus, the initial state effects alone can reproduce more or less the ground state data, but for the excited to ground state data, you need to apply final state interactions. So then we thought about the probability to have some kind of interaction also in proton-proton collisions. This is motivated by the fact that this division between proton-proton, proton-nucleus, nucleus-nucleus, the old paradigm of the 3 different systems, clearly isolated, was at play up to 2012. Since then, there is a whole community also working on small systems. That means the following. In fact, this idea of a small system is that there are some effects. I'm not going to read the whole slide, only to say you that some effects that were considered to be exclusive of nucleus-nucleus appear in proton-nucleus and proton-proton collisions at high multiplicity. Maybe you already got some seminars, or you are working yourselves on the RHIC, the flow. There are some phenomena considered to be exclusive of nuclei that are in proton-proton at very high multiplicity. And particularly, we were interested by this plot that appear in quark matter. In this plot, LHCb showed the result on the exotic state X3872 over the psi prime, the charmonium 2s. And they show that in proton-proton, proton-proton collisions usually at this energy, 8 TeV, have a minimum bias multiplicity. Here's not the multiplicity, are the Bellot tracks. This is similar to the multiplicity. That the minimum bias value for the multiplicity is around here, and you obtain an integrated value here of 0.1. But they show that doing a study on multiplicity, they obtain a reduction of this ratio in proton-proton collisions according with the multiplicity. So our idea was to apply in this interaction with comovers that already applied before, successfully applied before for quarkonia in proton-nucleus, for the high multiplicity events in proton-proton collisions. So for this, we applied the same formula for the interaction cross-section. We do an average over the Bose-Einstein distribution of the comovers, and we obtain, these are the geometrical cross-sections, we obtain another different cross-sections that are very close to geometrical due to the, due to the small binding energies here involved. Why we are trying to do so? Okay, those results presented in November at Quark Matter were interpreted by the collaboration in principle as the fact that there was this exotic state could be a molecular state. We think that this corresponds to a tetraquark state. In fact, we applied our interaction, our final interaction with the movers, with the pions, and you see that in case of having a molecular state, the interaction cross-section is going to be very high. So most of the exotic X are going to be suppressed for multiplicities above the mean multiplicity. If you consider, instead of that you are having a tetraquark, the cross-section of interaction, the tetraquark is smaller, is going to be smaller, and you will obtain a behavior with the multiplicity which is consistent with the data. So our interpretation is that the data obtained by LHC collaboration show a tetraquark nature for the exotic X. You can wonder how did we do to apply this in proton-proton collisions. Well, as before, we consider that for collisions around the minimum bias, you have no effect, no final state interaction effect, since the multiplicities are not very high here. So you reproduce the mean value, but then if you have 3 times or 4 times the minimum bias multiplicity, you will obtain a suppression. In fact, this motivated us to apply this study to other results that we didn't pay attention before. Also from proton-proton collisions for the upsilon excited states over the ground state by CMS, for example, versus the multiplicity. And we just applied, we did that in 10 minutes, and the results were like this. So that were the results for the, I showed before, this is for the upsilon. So the results for the upsilon make us think that we are right, that there is an effect in high multiplicity proton-proton collisions, that this effect should be applied when you study excited over ground state for Quarkonium, and in particular, that if you apply this effect for a tetraquark X, you can reproduce the data. In case you consider the tetraquark as being much bigger, let's see, for example, a tetraquark has a size in between 1 and 2 Fermis. A molecule can be between 7 and 10 Fermis. There, By applying final state interaction with comovers, you cannot explain the data. So our conclusion is that the exotic X3872 is a tetraquark. What are we doing now? In order to prove that there is one point that was mentioned at the beginning, and that was the enhancement of quarkonium. So it's true that there are effects that can induce an enhancement of the quarkonium. Those effects are well known in nucleus-nucleus collisions, and were found by Ali's collaboration that showed that the GPSI could be increased by regeneration of CC-bar pairs. And so it is fair to wonder if this effect could not be at play in case you will have a molecule here that could be increased. So we think that no, not even in that case you will obtain this behavior, because together with Alessandro, we are doing the following, and this is the last part, this is the last slide, in fact, is that in case you consider secondary charmonia production, so these regeneration effects, that in principle are not expected to be at play in proton-proton and proton-nucleus. But imagine that you consider that the molecule is so big that maybe there is a phase space where you can apply those effects. In that case, you are not going to obtain a suppression according to LHCb results. You are going to obtain an enhancement with the number of charged particles, as you can see here. This is not for X over 2s. We didn't do it for the moment. We are working on that. We did deuteron over proton, considering that that could reproduce in some way molecular over non-molecular nature. And that is all I'm going to speak today. My conclusions, if any, is that there has been a huge amount of work trying to understand the nucleus-nucleus data for charmonium, for GPSI, since the GPSI was proposed as a quark-gluon plasma signature. In fact, the situation is much more complicated. You need also to study contemporarily proton-nucleus and proton-proton data. The proton-nucleus data can give us some clues about final collective effects, and the proton-proton data also about the nature of the medium and the exotic spectroscopy. So the quarkonium would be a hint of the confinement for nucleus-nucleus, but also a hint of coherence and a hint of QCD in that way. So another way of studying things is starting from here and going up to here. We studied the contrary, and that makes that this field for years has been a kind of too much complicated, more than it should be. And that's all from my side. And thank you very much for your attention.
Are there questions?
I have a couple, if I can.
Hi, Angelo.
So the first question is very naive. You might have said it and maybe I missed it. At the beginning, you presented three models, right? One is the non-relativistic QCD, yes, and the evaporation model, and another yes, one, right? Which I don't know. Now, and then you mentioned about NLO and NLO corrections models, right? Now, okay, for the non-relativistic QCD, I understand, meaning that it's an expansion in momenta and kinetic energies, so you just go next to leading order. But for the other ones, what is the parameter that determines what correction is?
Yeah. Okay. Order? Yeah. Okay. You mean for example, for the color singlet model? For the color singlet model, that I know a little bit, the parameter is the fact that they consider processes as in the first approach, in the leading order approach, they consider gluon giving CC bar. They introduce two processes, so orders in alpha S, in order to do correction. So they would introduce gluon given CC bar plus a hard gluon. That was the initial correction, and more like this. It's all I know. For the color evaporation model, it's not a leading order or next to leading order. The main difference that was developed in the last year was the fact that they introduced, instead of the parameter being the mass of the state, they introduced the transfer mass in such a way that they can introduce an independence on PT that, first of all, was not there. And in any case, for our region of interest, that would be up to, I would say, since up to now I worked in integrated PT results, the three of them are safe and give similar results.
Okay, good, thanks. And then I have another question, but this is maybe because I'm ignorant, about these initial state models, the effects.
Okay. Okay.
Here, if I understand correctly, you talked about them mostly from the point of view of the Quarkonium suppression, right? But if
yes, but they are there for anything. Yeah.
But if I remember correctly, so at the very beginning, I don't know, but a few years ago, they were introduced also to explain the anisotropies, right? All these VNs.
Yes.
But as far as I understand,
okay,
the problem is that if you assume that the VNs are due to initial state effects, then you are killed by hadronization. So,
sure.
like what explains the VNs? Given that you observe them in PP as well, if I understand correctly.
Yeah. Yeah. Okay. So there are 2 points here. One is this is the nPDF modification. The nPDF modification cannot explain a VN. Mm-hmm. The other initial state effect as a color glass condensate, as saturation, was the one introduced to explain VNs. And at that moment, along the first results were not very good. And then there was an approach by McLaren and Bjorgen-Sengen that introduced the asymmetry of the proton, the initial saturation, the asymmetry of the proton, and a hydro evolution without equilibration. Mm-hmm. Mm-hmm. And that one was successful in explaining VNs. So I think that part of this, let me show you, because in one of the slides, here. So this is the main question. Even for proton-nucleus or for proton-proton. In order to reproduce the flow, for example, that was studied in proton-nucleus, the initial state effects were used, is one of the contenders. The other contenders are the hydrodynamics, and there are many models that are putting both. I think that, I don't know if Dionysius is still in the, but maybe he knows also about this. But my idea, VN with nuclear PDFs, no way. VN with a color glass condensate plus hydro, yes. VN with initial state effect alone, only if you take into account kind of asymmetries, and I'm not the 3 components of the proton, but I am not very convinced myself.
Thanks.
And correct me if I'm wrong, but the main motivation for the nuclear PDF, basically for this initial state, was the MC effect. Basically, something
at the very beginning. Yes, you are right.
To inclusive measurements, right? So you are not sensitive to anisotropes in that case. It was related to DIS measurement, basically.
Yes.
In that case, you basically
right.
whatever final state effect, and you are more sensitive to this initial state. And that is still there, right. So you still need to include this initial state things.
Hi, Elena. I don't really have to add anything, but you quote me twice. So I really understand that there could be many possibilities of initial state effects, and kind of difficult to disentangle. I don't know. I mean, you know more than me, so I really don't have to add anything on that. Just because you mentioned me, so I'm here.
Because you know much better than me. This. The only point is that for the, I have to mention one thing. Okay, for the initial state effects concerning quarkonium, the color glass condensate is very successful in reproducing this. But be careful, because this saturation approach cannot be applied here in the backward region because of the saturation momentum. I am right, Dionysius? In any case, I have some, okay, I don't have them in this plot, but I have also the results from the glass condensate, and here they agree, but the rapidity region of applicability of the saturation, here you have saturation, here you don't have saturation. So the model, the framework of the color glass or the BKL equation is not applied here, okay? In any case, both are initial state effects that are applicable at mid and forward rapidities.
Yeah, definitely, yes. Okay.
I have a question as well. This concerns the last part of your talk where you discussed your evidence of the charmonium state, the exotic state, to be either a tetraquark state or a molecular state.
Yeah, or molecular.
Yeah, but I was surprised. I mean, these arguments are mostly geometrical, isn't it? And rely on the size.
It is true. It is true.
I mean, how well do you know the size of this molecular state? You know, 5 to 10 Fermis is gigantic. I mean, that is sort of like a lead nucleus. So how well do you know these? I mean,
I don't know very well, but I think that here.
You know pretty well. So the determination of the binding energy. Well, so first of all, this is related to the fact that the binding energy is very small, and you know this binding. So the binding energy is compatible with 0, and the error is of let's say 150 keV. Okay, so you know.
So the binding energies are well known.
Yes.
Yes. And it's so well known that it's 0 within the error, with a small error.
Mm-hmm.
Okay, so that tells you that the state, just by uncertainty principle, is huge.
Yeah, sure.
And that's why you get these gigantic numbers. And then,
but there's still
regardless of the detail of the potential, you still get large sizes of order of 10 Fermi, let's say.
But the cross section somehow is geometrical, right? It goes like R squared.
Yes. And makes sense, right? Because, I mean, the interaction with comovers doesn't know anything about the details of the...
So it's... there is... So it's a sort of black disk cross-section.
It's precisely about this.
Yeah. Okay.
And since it's inclusive...
In the last
you're just considering any possible interaction with any kind of comover.
But you have summing over all the possible final state to eventually expect something that scales as the geometric cross-section. Yeah. But somehow the uncertainty 5 to 10 Fermis, is not better known than that. I mean, if you know the binding energy very precisely.
Oh, I said I said that the binding energy, it's compatible with 0 with a small error. So that means that the size is any number from, let's say, 7 Fermi to infinity.
Yeah, it's 7.
So, I mean, because it's close to 0 and the uncertainty is large, that reflects itself in a big uncertainty in the radius.
Yes. So the absolute value of the uncertainty is small. But still it makes it compatible with zero. So basically you go at like the inverse. So.
I see. Mm-hmm.
Well, I mean, the point is that you choose a reference value, and if it's not right, it can be worse.
Mm-hmm. Because, I think that
the interaction.
Here we choose the same, since in the LHCD, when they present the results, they choose 7, and I took 7 to 10. 7, sorry, 7 to 10.
Okay.
Roughly, people use as a reference for the binding energy the error on the binding energy. You can think of that as a kind of lower value for the size.
Mm-hmm. Thank you very much.
Thank you to all of you for inviting me.